and today we're going to talk about the general search algorithms. So we've talked about search at a high level and how we can define our state and action space, and we've also talked about graphs. Now let's put that all together and figure out what the general search algorithms we will be using are. So this is our general problem. We're going to be starting from some start state and trying to reach this goal. And we're going to be changing this graph a little bit as we go to result in more interesting problems. But to start off with, this is what we're going to have. Now each one of these edges are bidirectional. You can go either direction, but we're mostly going to be thinking of it in the single direction case. This is the generic search algorithm we're going to be using. So we're going to have some graph, which is defined as our vertices and edges. So these are our states and our actions. We're going to have some initial state x0, which is some vertex. And what we're going to do is set some temporary variable x to our initial state. While x is not the goal, so while our current state is not the goal, and open is equal to nil. So we're going to have two lists. One is going to be called open, and one is going to be called closed. So open is the vertices that we're currently looking at or plan to look at in the future, and closed is the vertices we've already looked at. So we don't want to look at the same vertex over and over and over again because we have that bidirectional graph. We can end up in these cycles. So what this algorithm is going to do is kind of ignore that. It's going to handle the cycle by saying that if I've looked at that node before, don't look at it again. So then what we're going to do is we're going to do this thing called expanding a node. And what that's saying is that I'm going to search in that node. I'm going to look and see what's there, see if it's my goal, and then figure out what nodes are connected to it. So the first one we're going to do is once we've searched a node, we're going to expand it and add it to our closed list. So we're saying that our open list, the list of vertices we want to look at, is equal to the current open list minus the current vertex because I've already looked at it, plus whatever the successors of x are that I have not seen before, which is closed. So what this looks like is that if I have some node here, which is A, I'm going to essentially at some point have A added to my open list. And then when I go to expand A, I'm going to remove it from my open list, check all of the edges coming off A. Let's say I have these vertices B, C, and D. Now I've looked at D before, so I don't want to add that back to my open list, but I haven't looked at B and C, and I will add that to my open list. And then what I'm going to do is pull the top vertice off of my open list to look at next. And then I'm going to do this iteratively until I find the goal. So if I run out of vertices to search and I haven't found the goal, this loop will end and I will go to this if statement. And then since my current position is not the goal, I will return. But if I do find the goal, it will be the goal and I'll return that goal. What we're going to be doing in the background is building something called a predecessor list. So the pred list is how vertices are connected. So let's say I expanded A and I saw B. So I would say that B's parent, its predecessor, is A. And I'm going to be able to go through this. So then once I get to the goal, I can then look at my goal and go, all right, so my goal and the predecessor of my goal was this vertex B, which then goes to A, all the way go back to our start position. And then if I just invert these arrows, what I'll get is I go from the start to some vertex to A to B to G, which is our goal. And this is the path of nodes and edges that would get me from my start position to my goal position, where these are my states and these are my actions. Now let's talk about some properties of that. So there are two important properties when it comes to search algorithms. The first is completeness, and it's essentially will the algorithm find a solution if it exists? And the other is optimality. Will the algorithm find the best path? And remember, optimality can always be defined in weird ways, so we have to say, what is it optimal with respect to? Some will find the shortest distance, some will find the lowest cost. How we define that is the important thing. And the idea behind breadth first search is I want to search all of the vertices closest to my start position before moving on to the next level. So what I would do is I would search these vertices in one level, these in another level, and then finally this. And this prevents me from missing some shortcut or some possible path that I would like to use. So in order to implement this, our frontier or our open list is going to be implemented as a thing called a queue. And what that means is that the first in is the first out. So if I have some queue, just like a line you have at the store, and I put in like A, B, and C in that order, that means that I will search A first, then B, and then C. So to start off, we're going to have our initial state S, and that is going to be in our open list. We're going to expand that node and put that in our closed list. Then we're going to add its neighbors, A and B. So we're going to add A first, and then B. We're going to break ties in the alphabetical order. And then what we're going to say is we're going to expand A. So when I expand A, I now need to start keeping track of where I started from. So A's predecessor is S. And then once I expand A, I'm going to get C, who comes from A, and B, who comes from S, and A that comes from S. So it's a little bit easier to keep track of this in the open list, and then we'll just be adding things over to the closed list. So the next thing we're going to do is expand B, so B from S, and then we're going to get D, which comes from B, and E, which comes from B. And then I'm going to expand C from A, and I'm going to get G from C. Now I'm going to stop the search right there and say that this is my goal. So now what I'm going to do is look back in this closed list and rebuild my trajectory to get here. I'm going to start off with G, and then looking at its predecessor, I get C, and then looking at C's predecessor, I get A, looking at A's predecessor, I get S. Now the really cool thing about breadth first search is if I did this search in the opposite order, if I broke ties in a different way, I will still get the optimal solution. So that means that breadth first search is complete. I will always find a solution if there is a solution. And it is optimal. I will find the lowest number of actions to get from my start state to my goal state. So the lowest number of edges will be traversed using breadth first search. So the next thing we're going to look at is this thing called depth first search. So while breadth first search looks at all the nodes closest, depth first search will look at a random successor of the last node I searched. So essentially we'll go in a direction and keep going in that direction until it finds something or runs out of options. So our open list now will be implemented slightly differently. We're using this thing called a stack. The last in is the first out. So if I have A, B, and C, this is just like when you have those plates and you push them down. It has to be removed in the order of C, B, and then A. I cannot remove A first like I was doing for breadth first search. So let's look at our open and closed list and go through a breadth first search search. So to start off with, I will have our start state, and I will expand our start state over to our closed list. And then once I do that, I will have A and B. So I will push A first. A comes from S, and B also comes from S. Next, I will expand B. So I have B from S, and this will give me D from B, and then E from B. I will expand E from B. So now I have E comes from B, and from that I will get F comes from E. I will expand F from E, and I will get out G from F. Now that I've reached my goal, I can build my path back out. So I will have G goes to F, F goes to E, E goes to B, and B goes to S. The path I get out is S, B, E, F, G, which we know is not the shortest path because we did breadth first search, and that will give us the shortest path. We can also just empirically look that this is only going through 4 nodes and using 3 actions, while this is going through 5 nodes and using 4 actions. We want things with lower number of actions. Now, if I broke the ties differently and I searched down A first, what you could see from depth first search is that I would get out that path, which would be the optimal path. So that's the important thing of depth first search. It just depends on how you expand your nodes. You can potentially get lucky and expand very quickly, because in the breadth first search, remember, we have to expand these nodes and then all these nodes before we finally reach the goal. But in the depth first search, depending on how the search breaks out, I could find that in much fewer expansions, but I'm not guaranteed to find. So this gives us the depth first search property that it is not complete in an infinite graph. I'm not guaranteed to find a solution. The only reason we found the solution here is because you have a finite graph. So even if it was a complete dead end, depth first search would go down that dead end, add every node in that area to the closed list, and then backtrack out. And it is not optimal. We're not guaranteed to find any kind of path out of depth first search. It completely depends on how it works out. So in summary, there are at least 2 search algorithms that can be generalized in the generic search algorithm. And the differentiating factor for how search works is how the next state is chosen. In depth first search, I looked at a node that was connected to my last expanded node. And in breadth first search, I searched the entire area around my start state before moving on to the next level. So what you tend to see between the 2 algorithms is with BFS, you have this optimality property, but you have to search the entire tree at every level of depth. So this would be D equals 0, D equals 1, D equals 2, on and on. DFS, how it tends to expand is it searches in one direction, searches another direction, searches again, explores this whole area, then backtracks up, and then goes in a different direction. These two graph search algorithms have very different properties and come across very differently, and which one you would use depends on your application. If you want a fast solution, you might want to go with DFS, depending on your graph, but if you want an accurate solution, what you want to go with is BFS. So that's all for this video.